Good morning, everyone. Today, we are presenting a comparative case study titled Single Stage YOLOX versus Two Stage RCNN Family Object Detector using ByteTrack for multi object tracking. This project explores the trade off between detection, speed, and accuracy, particularly in the context of real time object or multi object tracking. Team details. We are a team number 5 members Jyotirmay, Ashish, Aman, myself Ayush Anand, and Dilip. Problem statement. Our problem statement is focused on advanced person re-identification using YOLO, deep feature representation, and ByteTrack. We aim to integrate YOLO-based detection, deep feature representation, and ByteTrack algorithm to evaluate how well these systems perform in real-world scenarios like surveillance or autonomous systems. Our referred case studies. First, our main paper, ByteTrack multi-object tracking by associating every detection box. It introduced the ByteTrack pipeline, which we are using. Second paper is a survey on deep learning based person re-identification method published in Image and Vision Computing 2022. This provides us with the insight into current challenges and solutions in re-identifications. Third paper is from ISCRM 2021, where YOLO and sorts were used for real-time traffic flow estimation. This helps us to understand the practical deployment of single-stage detector in time-sensitive application. Our next slide, fifth slide, yeah. Background and motivation. The background of our study lies in the trade-off between detection accuracy and speed. Single-stage detectors like YOLOX, they are extremely fast and efficient, suitable for real-time systems, but they sacrifice bit of precision, whereas single-stage like detectors like fast RCNN give high accuracy and precision, but they are expensive and slower. Our goal was to compare both of them using a unified tracking framework like ByteTrack and determine which is more suitable for real-time application. Yeah. Slide number 6. Yeah. ByteTrack. So what is ByteTrack? ByteTrack is a tracking by detection framework. Unlike traditional trackers that discard low confidence score boxes, ByteTrack keep them also. This dramatically improve identity consistency across frames, especially in crowded or occluded scenes or close-up scenes. It built tightly on top of YOLOX, making it perfect choice for evaluating single stage performance in tracking objects or tasks. Next slide. Yeah. ByteTrack tracking pipeline. So how ByteTrack works. First, YOLOX detects all the boundary boxes in the frame. Second, it split those boxes into high confidence, those split into two sets, one with high confidence, another with low confidence. In stage one, high confidence detections are matched with the existing tracks, whereas in stage two, those unmatched tracks are checked against the low confidence boxes. This two pass association helps recover from missed detections and occlusions, giving ByteTrack a bigger edge in crowded environment. With the foundation in place, I would like to invite my friend Dilip for the further slide. Dilip, over to you.
Okay. Thank you, Ayush. Continue the discussion. Let's compare the two main object detection strategy. First is single stage detectors like YOLOX predict bounding boxes and classes in single step. They are fast, anchor-free, and use a decoupled head of better training efficiency with ByteTrack. YOLOX can achieve around 30 FPS, which make it suitable for real-time application like drone or edge devices. On the other hand, two-stage detectors like faster RCNNs using regional purpose steps following by classifications, the result is higher accuracy and especially in crowded scenes, but also lead to higher latency and GPU usage. These step models are better suitable for application where accuracy is most important than speed, such as offline surveillance analysis. Next slide, please. Okay. So evolution matrix and mode 70 results. Now let's look at the evolution matrix we used. First, we use MOTA measure overall tracking accuracy. Second is IDF1 evaluates how well the system preserve object identities across frames. Third is HOTA balance detection and association performance. And FPS tell you how the fast motors is like 30 FPS or 29 point something. And right now, I am heading over the slides to my mate, Aman. Aman, your part.
Hello everyone. Next slide, please. Okay. From the matrices given stated by Dilip, we shall evaluate how well YOLO and recurrent CNN performs in it. We can see YOLO performs much better in multi-object tracking, whereas in identity preservation, most of both of them fares almost samely. Uh, and YOLO is much faster, using up to 29 FPS, while DeepSort, that is RCNN, only keeping up to 13 FPS. This gives that YOLO is much more faster and accurate, even with its single stage detection algorithm. Next slide, please. So computational load. YOLO uses much more less number of parameters, that is 25 million parameters, whereas RCN uses 40 to 60 million parameters. It uses 118 gigaflops, which is about gigaflops is about 1 billion floating point operations per second. This shows that newer algorithm like YOLO, even though it is a single stage algorithm, works very much faster and better than a two-stage algorithm. Next slide, please. So handling occlusions. Occlusions are basically when an object like a car or a human being goes behind a tree or a board. So half of it only is visible to the camera. This is the situation called occlusion. Uh, ByteTrack can handle this very well because it uses the low confidence score also to calculate the boxes, thus handling occlusion much better. Uh, now I give the presentation to Jyotiram for more insights and results.
Thank you, Aman. Now, let's look at some real world applications and the trade-offs between using single stage versus two-stage detectors. In edge computing and drones, where real-time speed and lower power consumption are crucial, YOLO-X with ByteTrack is the better choice because of its lightweight architecture and high FPS. For crowd surveillance or public monitoring systems, where accuracy and detection precision matter more than speed, faster RCNN is preferred. In autonomous driving, the right choice depends on the use case. If you need low latency, YOLO-X works well. If the environment is complex with frequent occlusions, RCNN may provide better continuity. So there's no one size fits all model. The trade-off is always been between speed, accuracy, and compute availability. Next slide, please. Okay, so another important insight is that ByteTrack's tracking module called Byte is not limited to YOLO-X. It works as an add-on to other detectors and trackers like JDE, Fairmont, and CenterTrack. For example, adding Byte to CenterTrack improved its MOTA by 1.3 and IDF1 by 9.8. This shows that ByteTrack isn't just a one-off solution. It can generalize across various architecture, improving tracking consistency and identity preservation. Next slide. Uh, we also tested ByteTrack's performance across multiple data sets. On mod 17, it achieved 80.3 MOTA. On mod 20, 77.8 MOTA. On Hive, 61.7 MOTA. On BDD 100K, 41.1 M MOTA. These results demonstrate ByteTrack's robustness and flexibility across different real-world environments. So I would like to invite Ashish for the practical implementation.
Thank you, Joy. So now that we have covered the theoretical underpinnings, let me walk you through the. Thank you, Joy. So now that we have covered the theoretical underpinnings of the project, let me walk you through the practical implementation. Before we dive into the code, let me show you the flow of the project. So we start with the input images from the video frames, which are then passed to the YOLO model, as we have already heard from my teammates. This YOLO model detects the objects, that is persons, and then there are two main models. One is ByteTrack and other is OSNet. So what ByteTrack does is, for every detected person, it tracks that person as that person walks or moves into the video. Whereas OSNet extracts features of those people. So the reason we are doing these two different things is that the ByteTrack is good at tracking people as they move, but it cannot re-identify the person if that person goes out of the frame of the camera, that is from the field of the view. Whereas OSNet extracts features and therefore is capable of re-identifying the person if it re-enters into the frame. So with that, let me show you the code as well as output videos. So first of all, these are the results. So first is same camera and different moment re-identification. That is, we are capturing the same person using same camera but at different time intervals. And you can see the results. So for example, these side-by-side images represent the same person that was successfully identified as the same person by the system. Whereas beneath you can see that same person is being identified but across different cameras. So for example, on the left, you can see that the camera angle has been changed, but same person is identified. So this is re-identification right at this moment. And the way we achieve that is through the feature maps that were detected through OSNet. So for example, for the person on the left, these are the active regions that were detected by our OSNet model, and it paid attention to these regions. And that's why it was able to represent that person uniquely through feature representation. So let me walk you through the code as well as some other practical implementations. So on your right, you can see the output videos, and I will show you parallelly what I want to show you here. I hope you can see the bounding boxes drawn around the people, the colored bounding boxes. The color represent the ID of that person. And the way we are achieving that is through the code written on the left. So these are the methods. So like draw rectangle method that you can see here is used to draw the rectangles around those detected person. But I bet that the most important probably is detecting bounding boxes first and then tracking those results into the video. And the objective was that, as you can see for the person here, there is a green bounding box on the left. The same person should get the green bounding box if viewed from different camera. And that is what we want to check. So let me walk you to the next slide. Just a second. Okay. So here is the accuracy metric. First one is the HOTA metric that you heard, that is higher order tracking accuracy. So it actually tries to align the bounding boxes that were detected and gives us the score. So as you can see here, we have got this HOTA metric of 69.86, And there are as well as there are other accuracy metrics like MOT 20, and the combined result is given beneath. So these are some of the state-of-the-art results that we achieved by combining two different techniques. One is ByteTrack and other is feature representation through OSNet. So that was all about our project. We tried to combine two different aspects, two different techniques, through which we try to improve the accuracy of person re-identification system. So with that, I'd like to conclude here by claiming that the results that we achieved by this naive technique that we used are better than the techniques that we had before. Thank you very much.